Right. So our next talk is a distinguished paper, Gradual Parametricity Revisited, and the talk is going to be given by Eric Tanter.
Okay, thank you. Thank you, Nick. So welcome, everybody. This is joint work with Matthias, who presented the first talk of this session, and Elisabeth, who's here at Popple. So I've used, as you've seen, gradual typing is about programming with imprecise types, right? So we have this notion of types that can be either fully precise, static types like int or int, or fully imprecise like question mark or anywhere in between. And therefore, there is this relation that, well, if you call it imprecision, then the symbol is in the right order. And gradual language, what it does is best effort optimistic static checking, if you want, backed by dynamic checks. So this optimism is captured by relaxing the static type relations that we are used to account for imprecision. So for instance, consistency is the relaxation of equality, if you want. So int or question mark is consistent with question mark or bool, but not with bool or question mark. And therefore, gradual languages give you a number of properties, or at least there are a number of properties that we like about them. One is the type safety, modulo runtime errors, as we've seen. The fact that on fully static terms, then the program is, the language behaves exactly the same as a static language, that it's expressive enough so that with the question marks, I can embed terms from whatever dynamic language I have in mind. And to talk about things in between, we have these basically monotonicity properties for the typing and for evaluation that are captured as the gradual guarantees. Okay, so gradual typing has been explored in a wide variety of settings. And in this talk, we are concerned about parametric polymorphism. And in particular, with the parametricity interpretation of polymorphic types, right? So this means that polymorphic types dictate uniformity of behavior. So for instance, if we have like 101 on parametricity, if we have a function, we don't know its implementation, we know it has the polymorphic type for all x, x, or x, then by parametricity, we know that this function is equivalent to the identity, which means that if we use it, instantiating at int and giving 10, then we know we should get back 10, even though we don't know how f is implemented. Just by knowing that it is well typed, we know that. So parametricity gives us a very strong type-based reasoning principle that yields very useful free theorems. So what is gradual parametricity? So let's go back to the same example. And now let's look at one particular implementation of this f function. So here it's big lambda x, lambda xx, and then applies some function g to x and true. So is this well typed? Well, it depends. In a way, we want to know whether f is actually parametric as its type says. And obviously, to be able to answer this question, we need to know what g is, right? So suppose g, we are in a gradual language, so g might be some value of an unknown type, question mark there, which might be, let's say, the embedding of an untyped lambda term like this function here, lambda a, lambda b, if b, then a, else a plus 1. So one way to intuitively think of that function, if you want, is that it's half parametric, right? If you always use it with true as second argument, then it's actually equivalent to an identity function, so there's no violation of parametricity anywhere here. So it's okay. F is using with true, so that everything should go fine, right? But somehow the fact that f is parametric depends on this usage of true in its body. If instead it would use false, then we would go through the other branch and we would do a plus 1, which in our example would be 10 plus 1, which would be type safe, but we would be, if we let this go, we would be returning 11 and therefore breaking the uniformity principle, right? So we've got a parametricity here, we should flag an error and say you can't do that. So here really what's the lesson and why gradual parametricity is more challenging than simple gradual typing, if you want, is that tracking type safety at runtime is not enough. We need some form of runtime sealing to kind of remember that if you've made some parametricity assumption, then things are black box and you can't use them as such. So there's been we are not the first to look at gradual parametricity, hence the title of this paper. Most notably, there are two languages that have been presented recently. One is LambdaB, which is a cast calculus, polymorphic cast calculus. So you have explicit downcasts in your language. It's not a source language per se, but it has parametricity, and FJ, which is a source language that compiles to similar cast calculus, let's say. So even though they are very similar, they're actually quite different, especially in their static semantics, and they behave in interesting ways in their runtime. So let's look at the static semantics and ask ourselves whether for x, XOR x is consistent with inter-row bool. Right? So even if we admit some implicit polymorphism here, that's a bit weird, and those two languages disagree on that, right? So LambdaB is not a conservative extension of System F. System F with implicit polymorphism would accept for all x, XOR x related to inter-row int, but not to inter-row bool. If we look at the consistency now of for x, XOR x with for x, XOR question mark, then the two languages differ again. This time, maybe the surprise is on the right-hand side. And this is because FJ uses a precision relation that excludes type variable from the relation. So those two types are not considered consistent. Now, if we look at the dynamic semantics, let's look at this example. We have the System F identity function that that's bound to a variable of a known type. And then we instantiate this function at int, and then we give it a Boolean. Surprisingly, to us at least, both languages accept this and reduce without errors to true. The reason being that instantiations on question mark are actually lost in the runtime semantics. In the slight variation of this example, let's give this System F identity function the type for x, XOR question mark. So because of the restriction on precision of FJ, you would need to go through an intermediate ascription to question mark to get this to type check. But otherwise, the behavior of both languages is the same. If we instantiate the function at int and give it 1 and then do +1, in both cases, we don't get 2 but runtime errors. The reason being that the application of f here returns a value that is still sealed and therefore still unusable. And this despite the fact that we started with a System F identity function, which is a fully static term, and therefore there are no parametricity violations in this program. So that led us to reconsider the question and see whether we could get guidance from the abstracting gradual typing methodology, which was designed exactly for this purpose of helping designing gradual languages. So this leads us to GSF, which is a new gradual language with parametricity. So before entering into the details, let me just give you the end result. How does it behave on all these examples? Okay, so clearly is a different point in the design space. So first, it's a conservative extension of System F, so it doesn't relate inter-row bool with for x, XOR x. It uses the natural notion of precision consistency, meaning you just can put question marks everywhere, and that leads less precise things. It does respect explicit type instantiation, even on unknown types. And finally, it returns 2 in the last example because it uses it provides programmers with a notion of type-driven sealing that I'm going to explain now justifies that this program shouldn't fail. So basically here, if we take our example, we have this System F function. If we look at the type of the lambda inside is XOR x, and therefore the types tell us that we are justified to both seal on entry and unseal on exit, which is different from that term, where here the big lambda term is not a System F term, right? There's an ascription to question mark inside. And here the type of the lambda term is XOR question mark. So now the types tell us that we are justified to seal, and we should seal because it says parametric on the argument, but we are not justified to unseal because the types hide this from us. Why is this useful? Well, if you do a pair of two functions, a polymorphic pair with two functions, the first one having this term of type x or question mark, and you do the dual one having type question mark or OX. Now what you get is a pair of sealing and unsealing functions similar to what you have in the lambda seal calculus, which is basically untyped lambda calculus with sealing and sealing, dynamic sealing and sealing primitives. So a way to think about GSF is as a gradual language that ranges from system F on the one side to a lambda calculus with sealing primitives on the dynamic end. So that's for the basic idea of the language. And so how did we design GSF? We applied the abstracting gradual typing methodology that was mentioned earlier in this talk, and that has been applied already to a number of challenging typing disciplines like refinement types, effects, and security types. And so we feed this methodology with system F as our starting language. And we then give a definition of gradual types, a Galois connection that I'm going to come back to. And this, by following the methodology, gives us a definition of a gradual counterpart of system F with the type system and runtime semantics. But as you've seen from Matthias' talk, we still, once we apply the methodology, we still need to look at the language we obtain from this application of the methodology and see whether what properties it has. And maybe we need to do some adjustment if we want to have parametricity, for instance. Okay, so one small trick to start with is that we start with a formulation of system F that uses type names for instantiated type variables instead of substitution, and that's basically building on prior work. We know that if we use type substitution, we will confuse type instantiations at runtime, so we need to start from that one. And to simplify the problem and make it clear to how to derive the semantics, we focus on explicit polymorphism. So the type abstraction and type application are explicit terms in the language. As a result, the gradual language we obtain does not gradualize the term structure, so there's no implicitness in it, but I'll come back to that later. Okay, so regarding the interpretation of gradual types, so AGT sees a gradual type as abstracting a set of possible static types. And we just need to extend the standard definition of the concretization function to deal with type variables, which are a piece of static information, so this concretize to their singleton. And for recursive type, we just recursively interpret. That's as simple as that, and that leads us a natural notion of precision, in which you have a question mark at the top, static types at the bottom, and for instance, for X question mark, which is the type of all polymorphic terms, as less precise than question mark. And note that question mark or question mark is unrelated to for any polymorphic type because the head constructors do not match. One is an arrow and the other is a forward. Okay, so that was the easy part. The less easy part is the dynamic semantics. So AGT derives the evaluation of gradual programs by proof reduction, exploiting the Courier word correspondence. So when we type check a gradual program, we have a derivation tree. In this derivation tree, there are consistent judgments, like using consistency. And we can remember in the derivation tree why those judgments hold. So that's called evidence. And when we want to take a step that is simplify the derivation tree, we need to see if we can combine those pieces of evidence that meet each other through an operation that's called consistent transitivity. And either this justifies the transitivity argument and we get another reduction with which we can proceed, or consistent transitivity is undefined, and that means we have a runtime error. So that's like the cast errors through Courier word, if you want. So what we explain in the paper is that if we use the standard AGT definitions for consistent transitivity and evidence, the basic ones, we get a language that by construction satisfies type safety or the embedding properties, the static and the dynamic gradual guarantee. Unfortunately, it doesn't satisfy parametricity because of an excess of optimism, if you want. So how to go beyond type safety? We need to do some adjustments. So normally evidence is a pair of gradual types that capture the most precise information we know about a judgment. Here we need to refine this, the representation of type names inside evidence so that we keep local binding information that can get more precise than what the global store of type names has. And then to introduce sealing in the language, certain evidences get a special meaning, a special interpretation. So, for instance, an int or alpha int, int alpha int is a seal evidence that says that that's an int value, but that is like sealed with alpha. And dually, there's the unsealing evidence. And when those two meet through consistent transitivity, then we are justified to erase the type name and basically obtain an actual unseal. The problem with the standard interpretation of consistent transitivity is that it would give us optimistic unsealing. So we would unseal if it's possible that the evidence would represent an unseal, and that's too optimistic to ensure parametricity. So we need to strengthen this relation to this operator to preserve seal until they meet definite unseals. As a result, GSF is a type-safe conservative extension of System F, where well-typed terms are relationally parametric. For this definition of parametricity, we use a step index script-key logical relation that's basically the direct adaptation of prior work to the context of evidence instead of cast. GSF satisfies the static gradual guarantee, but it doesn't satisfy the dynamic gradual guarantee because what we do to recover the parametricity is in conflict with relational parametricity. And we show in the paper that based on the definition of precision and parametricity that we are using, the two are actually incompatible in this setting. This being said, not all hope is lost. There's a nice result that says that embedding System F terms at imprecise types actually preserves their behavior. Another way to say it is that imprecision on terms of closed types is harmless. And this result allows us to revisit certain free theorems in a gradual setting. So basically the question being, what are the free theorems of imprecise types in this case? So there were a number of claims and discussions in the literature whether, for instance, whether values of type for X question mark OX should always fail, or XOR question mark should be constant or fail or seal. We realize that all these behaviors are permitted by the parametricity relation, but they are not imposed by the parametricity relation. So it's perfectly fine to have a runtime semantics that fails always, because basically, if everything fails, the relation holds. But it's not imposed. And indeed, in GSF, those types have non-failing inhabitants, which are basically the System F identity function ascribed to those types. And there are more terms that can be ascribed to those types and that never fail and are not constant either. So we don't have like very interesting free theorems when we have gradual types, but we get some cheap theorems, so that's not as good as free, but not too bad. So for instance, if we have a value of type for all x question mark OX, and we know that its head constructor is lambda x question mark, then we know that this guy must always fail. That's definitely imposed by parametricity, and it's independent of the body of the function, so it's still kind of I'm finishing. I'm going to skip these quickly just to tell you different perspectives. So I'm going to skip this one. But the main limitation of GSF so far is thanks. Okay, so the main limitation of GSF so far is the fact that it doesn't address implicit polymorphism. So we have a solution to that basically means giving the flexibility of implicit polymorphism during evaluation. So I can tell you more about that if you have questions. We're looking into extending GSF with more language features like existential references and recursive types, and generalize this embedding theorem I mentioned. Another future work is how can we derive a space-efficient lambda cast calculus, for gradual parametricity, and to study whether other forms of parametricity can be reconciled with the dynamic gradual guarantee. And that's the summary of the talk, and GSF is implemented and available online, and I'm available for questions. Thank you.
We have a couple of minutes for questions.
Thank you. So in both this talk and the other one, you said, you didn't have some desirable soundness theorem, so you changed the semantics you got out of AGT. Were they analogous solutions? Were they the same solution? Is there some commonality between them that you could make more formal?
Yes. So in both cases, the violation of the relational property comes from, let's say, an excess of optimism or loss of precision in evidence. So in both cases, there was a part of the solution was to make the domain of evidence, which the original AGT paper allows, be a bit different and a bit more precise abstraction than the actual abstraction you use in the source. In the static system. So for instance, label intervals are a more precise abstraction of labels than gradual labels are. But then there are also differences. So the issue with implicit flows is different, and the solution needs changing the runtime semantics of the language. Here it's just strengthening the consistent transitivity aspect.
Thank you.
So the key to getting the parametricity was going with those evidence that had the ceiling, and that kind of reminds me a little bit in the blame calculus, the polymorphic blame calculus. We have two kinds of casts. One of them is the regular kind that deals with the dynamic type, and then there's another kind of cast in there that deals with type variables and sort of exposing or hiding the type that they're bound to. It seems like there should be some kind of relationship between the two. Have you thought about that? Or?
So I agree there should be, and the answer is no. I haven't thought more about that. That would be an interesting thing to look at.
All right, let's thank the speaker again.